Say, do we really need more functions than we have enough? Or polynomial functions, absolute value, radical, rational, isn't that enough? Well, the answer is no. The answer is no, because functions in this chapter, in chapter 4, deal with other situations in real life that happen in real life. For example, let's say we have a turkey in the oven for Thanksgiving, and we want to, it's cooked, and we take it out and we put it on the counter. When we put it on the counter, the turkey starts cooling down, right? Well, cooling down, the temperature what happens every minute if you want, cooling down of the turkey is not going to use a polynomial function, rational, or any other function. It will use a function that I will present to you today. Here's another example. Bacteria, they grow. The function that models the growth of bacteria is not rational or linear or polynomial. It's one from here. The same thing with bats or rats or mice. They all grow. The population in general grows using a function from here. Here's another very sad situation when somebody dies. The time of the death is determined with a function from here, not with a rational, not with a polynomial, not with a linear, and so on and so forth. So a lot of applications in here. Another example, when we get a loan or a mortgage, which is also a loan for a house, the rate per month, what we have to give back per month, is determined with a function from here, not with what we learned so far, which means rational, polynomial, absolute value, radical, no, with a function from here. So that's why these two functions that we're going to look at in chapter 4 are very, very important because of their wide applications, okay, in real life situations. So let's start with chapter 4. Today is the 10th. In chapter 4, we will look at two functions. One function is called exponential. Exponential function. The other function will be the inverse of this function. And these are the only two functions we are going to look at in chapter 4. So the first function is the exponential. And then when we are done with the exponential and graph it and understand what it tells us, then we're going to look at its inverse. Okay, ready? Can anyone name this function for us? What type of function is it?
Exponential function.
It cannot be exponential because it has a square root of x. It cannot be rationally because it doesn't have a fraction. So then what function is it? It cannot be linear because it has the square root on top of it. So first read the function. Read it and then you will identify it correctly. Do you say over something? You don't. It's a square root, of course. Why is this called a square root? Because it has a square root. Okay, very good. So here's another one. What type of function is this? Read it first and then identify it and tell me, well, this function is blah, blah, blah. What function is this? Of course, because it has an absolute value in it. Okay, finally, I'm going to ask you, how do you think this function, or maybe this function, would be called? We have not seen these two functions. Why is it exponential? Because the variable is the exponent. The variable is the exponent. Okay? So both these two have two pieces. The first piece is the base. And the second piece is, very good, the exponent. Here, this is the base. And this is what again? The exponent. Very good. Again, we have not seen these functions before. I'm saying two functions because look at what happens. The base here is 2, and the base here is 1/3. You remember we had two shapes for x squared. We had the shape in which the function has a minimum. That was positive x squared. And we also had the other shape, which was negative x squared, which means the function has a maximum, right? Same thing here. We will have two different shapes. Before we analyze these two functions, I'm going to ask you this question. 1 to the 3rd power, 0 to the 4th power, and let's say -2 to the 3rd power. Am I able to raise 1 to the 3rd power? Yes, and the answer is correct. Am I able to raise 0 to the 4th power? And the answer is?
0.
Good. 0 times 0 times 0 times 0, I can get 1. Is that okay? Good. And the last one? Yes? Correct. It is -8. Very good. Perfect. However, the reason I'm asking you this is because I will make a point in explaining that these are not allowed in an exponential function. What is not allowed? What is not allowed is a base of 1. What is not allowed is a base of 0. And what is not allowed is a base of negative. So what can the base be? The base of an exponential function can be either a greater than 1, strictly greater than 1, not equal to 1, or a tiny positive number, not 0 and not negative. These are the only two possibilities for the exponential function. As I gave this example, with a base greater than 1, right here, this is the base greater than 1, and with the base between 0 and 1, which is here, 1/3. Okay, and as expected, with x squared and negative x squared, we're going to look at two different shapes. Good. So remember, this is the base. This has nothing to do with the domain of the function. This will give us the domain of the function, values of x. This is a fixed number, which is given to us either to be greater than 1 or between 0 and 1. Has nothing to do with the domain. So I would like us to first start by analyzing the graph of 2 to the x. Okay. Whenever I'm asked to graph a function, what is the first question I have to think of?
You gotta think in the range, the domain.
The domain. Perfect. But also before that, absolutely correct. The domain is the key. But before that, I'm asking myself, what am I graphing? What is this? Because if it's polynomial, I know I'm going to have to graph something like this. If it's rational, I'm thinking of horizontal asymptote, vertical asymptote, blah, blah, blah. If it's quadratic, then it's this or this. If it's linear, it's this or this. So what type of function is this? If it's absolute value, it's a v function. If it's a square root, I know how to graph it. So what am I expecting here? I don't know the graph yet. But I should say to myself, oh, it's exponential. Good. So now let's find the domain. So in order to find the domain of a function, we are asking ourselves, what can I really plug in x? What can I really replace x by? So let's look. Can I raise 2 to the 2nd power? And I get 4. Good. Can I raise 2 to 0? And I get
0.
Right? Any number raised to 0 is 1, except 0 raised to 0. So any number raised to 0 is 1, not when the base is 0. Good. Now, what if I can I plug in x? Can I replace x by -2? Can I determine 2 raised to -2? It's 1 over squared, right? Right? So then what is the domain of this function? We plugged in positive, we plugged in 0, we plugged in negative. Say it again.
-2.
So one more time. We plugged in positive, numbers, we plugged in 0, we plugged in.
Negative infinity to infinity.
Exactly.
All
So
numbers.
we will put this function in the category with polynomials. It's not polynomial, but it has no restrictions on the domain. It's a friendly function. We like it. I don't have to think about its domain. It's defined everywhere. So the domain is all real numbers. We're going to write this a couple of times today. Exponential functions, friendly. How friendly? Like polynomial functions. No vertical asymptotes, no no restrictions on the x. I don't have to solve an equation or inequality to find the domain. No, all real numbers. Good. So now let's pick some values. I'm going to pick -2, -1, 0, 1, and 2. Because I want to see how the graph looks like. Okay, so now let's plug in -2 in the function right here. And tell me how much is 2 raised to -2. One over 2 squared. Yes, 1 over 4. Very good. Is this clear, everyone? Yes? Jesse? Okay. We know a property of exponents. A raised to -n is 1 over a to the nth power. So when I want to find 2 raised to -2, I have 1 over 2 raised to the second power based on this property. And then I get 1 over 4. Better? Everyone? Okay. Don't let me move on if you have questions anytime, okay? So this, yes, of course. So when we raise a quantity to a negative number, this really means a fraction. It's a hidden way of saying a fraction. Good, so we get 1/4. Is this okay now, everyone? Okay, so now please plug in -1 and tell me what you get. So now the x is -1, so I can determine the y value. Yes, I think that's what you said, but I didn't hear it. I'm sorry. Good, let's plug in 0, please. Let's plug in 1, please. Let's plug in 2, please. Good. Now remember, the next item on the list should be the end behavior. For this particular function, not for the previous ones that we looked at, although in some cases it works, I'm going to determine the end behavior by looking at the pattern. So let's look at the pattern. I'm doing this way. I'm dividing a pie to 2 people. They get a lot. I'm dividing into 4. They get a little less. I'm dividing by 8. They get a little bit less. I'm dividing by 16. They get a little less, even less, each individual. And I'm dividing by 32 and by 64. And by the time I end up with everybody, how much will you get? Almost? Almost nothing. Very good. That's the answer. Almost nothing. Now let's go this way. 1, 2, 4, 8, 16, 32, 64, 128. Where am I going this way?
Get larger.
Say it again.
Get larger.
Larger and larger. That means infinity. Indeed. Now, when x approaches -infinity and the y values approach 0, what concept is this from the previous chapter? When x goes to -infinity and the y values get closer and closer, closer and closer, closer and closer to 0. What concept is this? What does this function have? If when the x values go to -infinity, the function values get closer and closer to a number, in this case to 0. What is that concept? What does it say? Horizontal asymptote. You forgot from the previous chapter? So y equals 0 is a horizontal asymptote at negative infinity only, right? So this function has a horizontal asymptote. We have never seen this before. We're going to graph it in a minute. So this function has a horizontal asymptote on one side, but not on the other. This is a very special function. Okay, so let's graph it. Do you remember this? Type 2, y equals 0? Okay, very good. So now let's graph it.
Excuse me.
Yes,
I thought you said that there's no vertical asymptote, no horizontal.
vertical asymptote.
You said there's
That's
no
when the function is undefined. Vertical asymptotes. This is a totally different situation that has nothing to do with the domain, right? So function is undefined, and then it potentially has a vertical asymptote. But this function is defined everywhere. The function values, the y values, approach something when x decreases without bound. Good, very good question. Good, so please give me the first order pair you want me to plot.
-2, 104.
Very good. Kind of difficult, I'm going to say here. The next one. Next one.
0, 1.
0, 1,
Very good. Next one.
1, 2.
And so on and so forth. So this is a graph of 2 to the x. We have a lot to say about this function. Number one, give me again the domain of any exponential function. One more time so we can write it down. Very good. Now please look at the graph and give us the range. The range is right here, right?
0.
That's where the range should be, right?
Mhm.
And
0 to the range.
and you can determine it from the graph. So tell me from the graph.
0 to 4.
0 to infinity, right? Look, it doesn't stop. It goes on forever. I have an arrow here. So 0 to infinity. Is this function increasing? All the time. All the time. Number 4, x-intercepts. What can you say about the x-intercepts of this function? None. Very good, of course. Number 5, the y-intercept. Can anyone give us the y-intercept of this function?
0, 1.
Very good, awesome. 6, is it 1 to 1?
Yes.
By the horizontal line test is 1 to 1. Very good. Does it have an F inverse? Which functions have?
Yes.
Yes, because all functions that are 1 to 1 have an inverse function. Very good. Good. 8. Horizontal asymptote. Yes, Damon?
0.
Yes, not 0. Y equals 0 at negative infinity only. Good. So can you please give me a couple of maybe 3 ordered pairs so I can graph the inverse? We don't know anything about the inverse yet. But I know that I have to graph y equals x when I graph the inverse function of a 1 to 1 function. And then please give me 3 ordered pairs that I should be using to graph the inverse.
How do you pick up the inverse? Y equals x. I mean, that's what you.
No, this is not the inverse. We know from chapter 2 that the function and the graph of the inverse will be symmetric with respect to y equals x. So when I graph both, I will also graph y equals x. If I graph the function and its inverse on the same coordinate system, I have to graph y equals x as well to show that if I fold that graph, then I have the same. Yes, this is not the axis of symmetry. The axis of symmetry is characteristic to one function only. Which one? Which function is the only function that has an axis of symmetry? Very good. Awesome. Very good. Thank you. Good. Awesome. So can anyone give us 3 ordered pairs so I can graph the inverse?
1, 0.
Very good. 1, 0. Here it is. Awesome. Another one.
2,
Yes?
2, and 1.
Exactly. I only have to reverse the coordinates, right? Because if the function is defined on A, taking values in B, the inverse is defined on B, taking values in A. Very good.
4, 2.
4, 2. And also I need 1 in here. In the same.
So you got 1, 2.
1/4, -2.
1/4, -2. So if this is 1/4, here's -2. Very good. Very good. So you notice that if the base of the exponential function is greater than 1, the function is increasing. What can you say about its inverse? Will the inverse be also increasing? Absolutely. If a function is 1 to 1, it's increasing. Its inverse will also be 1 to 1, and it will be increasing. Any questions? Okay, I would like to look at a couple of maybe one problem with transformations. So let's say we want to graph this -2 raised to x plus 1 and plus 4. We want to graph it using transformations. Graph using transformations. First, I have to identify the base function. Not to be confused with the base. Just the simplest possible function that I used to create this. Which function did I use to create this function? And you can say, okay, did you use the absolute value of x? No. Did you use the square root of x? No.
-2 the exponent.
Correct. But then the negative in front is one of the transformations.
So it'll be 2.
Exactly. Yes. This is the function that I used to create this. Very good. Then the first transformation on the base function is say it again, Jesse. Perfect, exactly. So number 2 is 2 raised to x plus 1. Indeed, left 1. Awesome, very good. See, this is what we studied a long time ago. Number 3.
Plus 4.
No, I cannot do that. In order of operations, I cannot.
Oh, reflection.
Yes, indeed, -2 raised to x plus 1, reflect with respect to the x-axis. Very good. And the last one, number 4, is -2 raised to x plus 1 plus 4. So this is indeed up 4. Very good. Awesome. So let's go step by step. How do I graph 2 to the x? It's a function that has a horizontal asymptote at -infinity, and it blows up on this side. This is what I have to graph first. Correct? Okay, perfect. So let's graph the base function. Where does it cross? Always. All exponential functions base, simple, no transformations on them, must cross the y-axis where?
0,
Comma.
0, 0.
It cannot, because it cannot be 0.
Oh, okay. Will we be looking at 2 then? So
When x is 0, how much is this?
1.
That's it. So all exponential functions, if they have no transformations, pure exponential functions, when x is 0, the function value is 1. So yes, it will cross. So this is 2 to the x, and it has to cross at 0, 1. And this is an arrow. Perfect.
You say all transformations must
Not
cross?
transformation, all pure exponential functions. When you plug in 0, you get 1 for all pure exponential functions. Good. Then you told me left 1. So here's my marker. Where will I move this point? Left 1.
-1.
Exactly, right here. From 0, 1 to -1, 1. So here's the next graph. This one in blue is 2 raised to x plus 1. Then you already told me what to do next. What will I do next? One more time. Reflect. So where will my marker go?
Down.
Exactly to which point?
One negative one.
Negative 1, negative 1. Very good. Negative 2 raised to x plus 1. Then, final step, you told me to do what? Up 4. Now, let's analyze this for one more time. One more time. There is a horizontal asymptote at 0 for all these three functions. That didn't change. But now, I want to move the graph up 4 units. What has to move first? So the original horizontal asymptote is y equals 0. If I move this graph, the horizontal asymptote has to follow the graph because I moved the whole thing. The horizontal asymptote doesn't change. It's still there, in other words. But if I move the graph up 4, I have to move the horizontal asymptote as well up 4. So this is 1, 2, 3, and this is 4. This is y equals 4 from y equals 0. And where will my marker go? This point that I consider or called my marker, where will it go? From negative 1 to negative 1, comma, 1, 2, 3, 4. 1, 2, 3, 4. So not at 2, but at 3. 1, 2, 3, 4. Correct? So now I graph. And this is final. So this is f of x equals negative 2 raised to x plus 1 plus 4. As you notice, this function crosses the x and the y axis. It does. I don't know where. I haven't studied that yet. I can. And we will get to equations, not today, but on Thursday. Okay. Any questions on this graph using transformations? Now, if I only ask you, for example, just give me the range of this function, what will you say? Of the final, not the components. What will be the range of the final function? Yes, Damon?
So
Are we talking about the same
negative
one we just did?
I'm talking about the final function that we just graphed.
Right, so there's the f of x, negative 2, and you said the final range, if the final range is negative.
I only want to look at this function, the one that we just graphed finally,
Right.
and I want to identify the range of it. I don't need the components. I don't need the range of the components of the function.
plus negative
That's what I'm saying.
Negative infinity 4
It's a 4.
to positive 4. Very good.
That's what I was trying to say.
Okay, very good. So negative infinity to 4. Perfect. That's the range. Awesome. Very good. So now I would like to continue with the other shape, because of course there is one more. So let's look at f of x equals 1/3 to the x power. Is this a pure exponential function, or does it have transformations in it?
That's
Pure exponential. Very good. So what will be the domain of any pure exponential function? And not pure still. Yes. Good. So let's plug in the same numbers, negative 2, negative 1, 0, 1, and 2. So we can graph this function and have an idea of how it looks. So please plug in negative 2. And we are using the same property. 1/3 raised to negative 2. What will that be?
3 over 1.
Yes, 3/1 squared. Good. So that is 9. Good. So let's plug in negative 1. What do we get?
6.
3. Good. Let's plug in 0. That's okay. Very good. Let's plug in 1.
1/3.
Very good. Let's plug in 2. 1/3 squared is 1/3 times 1/3. 1/9. Again, we want to see where we go. left and right. So 1 over 3, 1 over 9, 1 over 27, 1 over 81, 1 over 100. Where am I going this way? Perfect. Indeed. Let's go this way. 1, 3, 9, 27, 8. That's it. What does this mean about this function? What does this say about the function? Y equals 0 is a horizontal asymptote at infinity only. Very good. At infinity only. So one shape looks like this if the base is greater than 1. And the other shape looks like this if the base is less than 1. Decreasing everywhere. We're going to graph it right now to look at it. Good. So please give me the first ordered pair I should plot to graph this function.
-2, 9.
Very good. Indeed. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Next one. -1, 3. Yes. 0, 1. And then I get in trouble, of course. They're too small for me to graph them. Good. So what do we know about this function? Everything we knew about the previous shape. The only difference is that it's not increasing, but is decreasing on all its domain. That's the only difference between the shapes. Okay, perfect. Does it have, is it one-to-one? Yes, which means it has an inverse function. I have to graph y equals x when I graph f inverse. Since this function crosses y equals x, at the same very point, the inverse function has to cross as well. Because when y equals x means 2, 2, 3, 3, 4, 4. And if I reverse them, it's still 2, 2, 3, 3, 4, 4. Excuse me. So please give me a couple of ordered pairs so I can graph this function, the inverse.
1982. Oh, sorry.
Say it again.
1902.
Yes, when x is 1/9, 2. 1/9, 2. Another one.
1/3, 1.
Very good. 1/3, 1. Yes.
90.
Very good. That's good enough. I'm happy. I'm happy with this. And this is f inverse. So what have we noticed already? If the base is greater than 1, both the function and its inverse are increasing. If the base is less than 1, both the function and its inverse are decreasing. So please remember that. Good. I would like to look at an application. Compound interest. An application in which the exponential function is the key. Okay. Interest is compounded n times per year. Bless you. In the second possibility, continuously. What does the concept of compound interest mean? Recalculated. The interest is recalculated n times per year. In the second possibility, the interest is compounded continuously every second. There are two different formulas. So I'm going to explain each and every piece. You do not have to memorize these two. They will be given to you. A equals P, 1 plus R divided by N, everything raised to the power NT. The continuously compound interest is P E raised to RT. Okay. So let's identify each and every piece. A is the accumulated value. P is the principal. So let's stop for a moment and just discuss these two for a moment. So we take a certain amount of money to a bank, and they say to us, look, we are compounding the interest every month. How much is N if we are told every month? How many times will they compound? 12. Very good. What if we are told we are compounding the interest quarterly? How many times per year would that mean? 4, and so on and so forth. Okay. What is the accumulated value? So for example, down the road, 10 years from now, 20 years from now, our investment, our principal, will grow to this amount, the accumulated value. P is the principal, what we deposit today. Okay, R. Yes, the annual interest rate. N, we already know what that means. Number of times the interest is compounded per year. Per year. And T is time in years. The same thing here. As you see, there is no N here because this formula compounds the interest continuously. So there is no number of times per year. I would like to look at a problem that will ask us to compare the two possibilities with different interest rates, and I'm going to add a question for the continuous compound interest. Okay, so we are on page, I'll find it, on page 475. So let's look at problem 56 on 475. Let's read it. Suppose that you have $6,000. I'm just copying the information, and then we'll identify which variable is represented by which number. Which investment yields the greater return over 4 years? And we have 8.25% compounded quarterly and 8.3% compounded semi-annually. Yes, very good. So that means N equals 2. And quarterly, you already told me, N equals 4. I'm going to add a question here, but we don't have to compare. I just want to, in addition to this, I would like us to find for, let's say, R equals 8.25%. I would like to find the accumulated value for continuously compounded interest. Okay, ready? Good. So first of all, what does 6,000 represent? I have to correctly identify each and every number. Very good. That is the principal. What does 4 years represent? Time indeed. Very good. T. Now we cannot use percent in these formulas. So I have to change it into 0.0825 and I have to change it into 0.083. But what does this represent? The rate. Very good. So this is one rate is 0.0825 and the other one 0.083. Very good. So now I'm going to put everything in the formula, which is 6,000, 1 plus 0.0825 divided by 4, and the power of 4 times 4, which is 16. The second possibility is 6,000, 1 plus 0.083 divided by 2, and everything raised to 2 times 4, which is 8. And the third one, which will not be compared to these, is 6,000 times E to 0.0825 times 4. No one can do this by hand. There's no such thing. So please go to your graphing calculator and let's put in 6,000. Parentheses, 1 plus 0.0825 divided by 4, close the parenthesis, caret, and the power is 16. I will repeat 6,000 in parentheses 1 plus 0.083 divided by 2 and the power 8. And then the last one, 6,000. Oops. Here is where E is. Second, here it is, right here, e to the x. Second, e to the x. And in parentheses, 0.0825 multiplied by 4. Close the parenthesis. So now, which would you advise anyone if they want to invest $6,000? Would you advise them to go for the first option, which is 8.25% for 4 years, or the second option, compounded quarterly, or the second option in which we are compounding the interest twice a year, but the interest is a little bit higher, which is 8.3%. Which one of these two would you recommend?
Whichever one compound the most. I mean, which one compound more frequently?
Well, you get the most money out of the third one in the long run.
Oh, correct, correct. But that's what I added in myself. So we want to make a decision between these two to answer the question. But you're right. If it's compounded continuously, then this will be better. So I'm going to write 8,345.81.
Put 6,000.
And then parentheses. Oh, for the last one?
Yeah.
Yes, yes, of course. So here it is, second, and here's e to the x right here.
Yeah. Okay. I mean,
And in parentheses, 0.0825 times 4. So you will advise the first one, right? Because it gives more money. So this is 8,317.84. And the second one is 8,306.64. So you will advise this because it's bigger than that. But yes, if the option for continuously compound interest at this rate is better than both. Any questions on this function? On the exponential function. So for now, we know that there are two shapes. One that is increasing on all its domain with a horizontal asymptote at negative infinity, which is y equals 0, and the other one the other way. Good. Now there are two special exponential functions. Special exponential functions. One of them is this. The other one is this. Why are they so special? I'll explain why. But first, let's look in the graphing calculator, because I want to show you where they are. So if you go to y equals and clear whatever you have in there. If you want to look at 10 to the x, here it is. It has a special key. So second, 10 to the x, and put x. Okay, so it's an exponential function with what base?
10.
10. So do you expect it to be increasing on all its domain or decreasing on all its domain?
Increase.
Right, because the base is greater than 1. Very good, has to be increasing. What about the other one, which is e? Careful, here's e again. Second, e to the x. What do we know about e? Is it a number greater than 1? Yes, it's the Euler's number, 2.71, and continues forever. So e is Euler's number, and is approximately 2.71, blah, blah, blah. And it's an irrational number.
how do you get that number?
How do you get the number?
I said, how did Euler's get his number?
Oh,
picked it.
here's what he did.
You
Well,
picked it.
yes, here's what he did. He determined limits.
Uh,
Yeah, that's not part of this course. So he determined the limit as x approaches infinity from a certain quantity, and he showed that every time he performs that operation, he gets e. There is another number that was determined experimentally, and I'm looking for my little thread. That's why I keep it every time. Okay, so here it is. So bear with me and say that this is a circle. I know it's not. Let's say, of course not. So let's say it's a circle. Bear with me and say that this is a circle.
mhm.
There are different circles, right? They're not the same. So how did they determine that pi, that they called pi? How did they determine 3.14, blah, blah, blah? What they did a long time ago, they measured the circumference, and also they measured the diameter. And they divided the circumference by the diameter, and they got 3.14. For this circle, they measured the circumference and the diameter, and the ratio was still 3.14. And then they looked at this circle, and they said, okay, let's measure somehow the circumference and the diameter. And they divide the circumference by the diameter, and they got 3.14. Same thing with Euler's number. Yep. So now if we want to graph these two, you can. Let's go to Zoom 6, and you will see here's the first function, 10 to the x, and here is e to the x. As expected, they are both increasing on all real numbers, right? Good. Okay, so now one other thing, since Damon asked, how do I determine that e? Here it is, second and division. See the e? And just press enter.
And none of it.
Oh, sorry.
Without motion.
So here it is, second and division, and press enter and you will get e. If you have any doubts or if you want to see pi and as many digits as the calculator will give us, go to second and the caret, it's pi, and press enter. Both are irrational numbers. There is no pattern whatsoever. They go all over the place. Any questions? Any questions? Okay, so our next step is to look at this inverse function. Oh, the names. I forgot to mention the names. So this is called the common exponential function. Oops. I don't know why I'm doing that. It's common exponential function. And this one is called natural exponential function. So when we look at the base e, it's natural. When we look at base 10,